Dear all, welcome back to Architecture and Programming Models for GPUs and Coprocessors. We're actually nearing the end of the lecture. We're still discussing GPGPU and CUDA, and we're currently pretty hands-on in that we're discussing lots of CUDA code. We started doing that in the last session, and we'll continue that today. And we might actually be able to finish the topic GPGPU today and might maybe even start discussing the applications part of the lecture where we talk about sorting on GPUs. And let's just start right away. Like last time, we discussed several different memory types. Like we had a look at how global memory is used and how you would allocate and how you would later free and then you would mem copy to device pointers. And this was the means in order to make use of GPU DDR memory. So basically the memory that is not on the actual GPU, like on the actual chip, but that is on the same board and that can be accessed with quite a high bandwidth from the GPU shader cores. And then we also discussed shared memory, which is actually a on-chip memory region, and which is much faster and with a memory access latency comparable to a small cache and can actually be programmed. And then we saw like a couple of examples, and one of them being the gem example, matrix-matrix multiplication, where we saw how shared memory can be put to good use. And the next memory region that we're going to discuss, that we already know a bit about, that we're now going to see how to actually use it in a CUDA program is texture memory. And texture memory is primarily meant for read-only access. Like there are also ways to write to textures, but for us it's actually not so important. Like this is not the most important use case of textures. And the texture memory is actually cached, and it's cached in a quite particular way. So that 2D texture accesses are quite efficient. There's dedicated hardware for texture filtering. So when we access a texture, then the GPU performs linear interpolation. Like this can be configured. You can also tell the GPU that you don't want to interpolate, but that you want to perform a so-called nearest neighbor lookup, which essentially just rounds the coordinate that is used for texture access, and then interprets that as an index into the texture. And in general, well, we can only use indices or coordinates into textures. That is, we cannot just obtain an address to the texture or to the memory that is associated with the texture. As like when we were able to obtain an address and a pointer to that memory, then we would also be able to figure out how the texture is actually arranged in memory. Like given a pointer, then we could, with very simple experiments, we could find out what the actual data layout of the texture is. And like this might be one reason why textures aren't addressable. So by not being addressable, the vendors can keep that a secret. So we're accessing textures. There are accessors, and we use those accessors, and we use texture coordinates in order to access textures, but we cannot directly address them. And today, like on today's GPUs, we use something that is called a bind-loss texture, which basically means there's an object, and CUDA calls those things CUDA texture objects. This is a special class, and the special class can be parameterized. So we set certain members and we set certain flags appropriately, and then the GPU can figure out how the texture will be used at runtime and how we filter inside the texture, and we can also tell it how a boundary handling is performed. And all that is done through the texture object. And this is in contrast to how GPUs worked before the Kepler architecture in 2012. Like before, we had a one-to-one mapping or a one-to-n mapping where there was a bit of abstraction on the software side, maybe. This is hard to say. But generally, there was a mapping between texture units and textures. So when the GPU, for instance, had 8 texture units, then there was also like a fixed number of textures that we could have in our CUDA program, like maybe a multiple of that, but actually a small number of textures only, like in that ballpark. And then we would have to, like if we wanted to have more textures than texture units, or than the number of textures that CUDA provided us with, then we had to combine multiple textures into one texture, giving us something that is called a texture atlas, which is actually quite hard to maintain on the user side. So today we don't need that anymore. So today we have what was called the bindless texture extension in DirectX or OpenGL, and in CUDA this was called a texture object. And this makes our life much easier. So when we use CUDA textures, we do that via the CUDA texture object type that I already told you about. And then there's a function that's called CUDA create texture object, which we pass certain parameters. Like one parameter is of course the object, and then there are other parameters that we can use to configure the behavior of the texture. And then we can pass those texture objects as if they were pointers. We can just pass them and copy them by value into the parameter list of the kernel. And inside the kernel, we can access the texture using those intrinsic functions, these intrinsic device-side functions. And those are basically access functions. So we don't directly obtain a pointer or an address here, but instead we tell CUDA that we want to access our texture object. And the texture object is a 2D object, and then we supply like a two-dimensional coordinate, like this coordinate here, that will access the texture at 0.3 and 0.4 in the x and y direction, and returns the floating point value there to texture. And like this coordinate for sampling isn't located directly on a grid cell, then the texture hardware will perform interpolation, and depending on how we configure it, it will perform linear interpolation. Like when we configure our texture objects, there is all that information that we gotta supply. We, for instance, gotta supply if this is a 1D or 2D or 3D texture. We also have to tell it what the texel type is that is associated with the texture. So if we're storing integers in 0 to 255, or if we're storing floating point values or even RGBA colors, for instance. We tell it the interpolation type, which is either point or Nebus-Maber sampling. So basically 0th order sampling, no real interpolation, or we can tell it that we will not perform linear interpolation. We can also specify if the coordinates that we use for accesses are normalized or not. Like when they are normalized, then they're just in 0 and 1. And when they're not normalized, then they're like within a range of 0 and some integer which corresponds to the dimension of the textures. And then we can also tell the CUDA create texture object function what rep mode will be used. Like for instance, when we use the rep mode clamp and we perform a texture access beyond the texture boundaries, like for instance, when we're accessing with normalized coordinates, and we use minus 0.1 for the texture axis and the rep mode is clamp, then the texture coordinate will basically be clamped to 0, or when we access with 2.0 and the coordinates are normalized, the hardware will clamp the texture coordinates to 1.0, or it might just use a constant border in that case, like assign it a certain color that we configured, like for instance black. Or it might perform a wraparound or a mirroring. So there are certain ways that we can define how accesses beyond boundaries are handled. So those accesses are well defined, as opposed to with global memory, where we would provoke a memory access violation, which might be handled in different ways by the GPU. And with textures, this is actually well defined. So we now talk quite extensively about the different memory regions that can be used with CUDA, and there are others, like we discussed local memory, which is basically just the same DDR memory as global memory, only there's just the memory region that registers are spilled into when we run out of registers. And there's constant memory. So those aren't so important to us at the moment. So now that we know how to use global memory, and how we use shared memory and how we use textures, this is already good enough for the time being, so that we can write more than just trivial CUDA programs. And from there we'll move on, and we'll now discuss the host interface, actually, like how the host interface is used, and in particular how we can make use of the asynchronous host interface. And I earlier already told you that kernels generally run asynchronously. And this depends actually a bit how we call those kernels. Like by default, when we use the default syntax that I showed you earlier, and we're just in the main thread, like the application is single-threaded, then the kernels will actually run synchronously and will block CPU execution, like which is not the default mode of the GPU actually, but the default mode of the CUDA API. So when we don't really care, then we will actually not make use of the asynchronous host interface. And this is actually also in contrast to certain other APIs, as for instance Vulkan, where those APIs are much more explicit about the host interface, or also, for instance, OpenCL is much more explicit about the host interface, and that we have to explicitly specify, like even when we don't care about synchronicity or asynchronicity on the device, even if we don't care about that, then we have to take care of submitting commands into queues and writing quite verbose code that has to do with the host interface. Well, with CUDA, if we don't care, then we just get a synchronous host interface. And if we do care, then we can use something that is called streams to submit into non-default queues. So with CUDA, there are those objects that are called streams. And since CUDA 7, we have, like when we're using a multi-threaded application, then we can also, via that, we can also make use of the asynchronous host interface, in that each thread will have its own default stream that compute kernels are submitted into. So we can make use of the asynchronous host interface by using multi-threading. But we learned earlier that the asynchronous host interface actually doesn't have much to do with whether our application uses multi-threading or not. So it's basically just a property of the interface between CPU and GPU, but CUDA helps us with that in a sense as that when we're using threads, then we have a default stream per thread, and then we have overlapping kernel calls just because we're using threading. But you don't have to use threading in order to use the asynchronous host interface, but we can instead use streams. And in order to use streams, we specify the stream that we're submitting into as the fourth default parameter with that peculiar angle bracket notation to call kernels. Like when we want to submit into a stream, then we specify the stream that we want to submit into as the fourth kernel parameter. Like consequently, that we then also have to specify the shared memory size. Like even if we don't use shared memory, then we will just pass 0 there, and then we can pass the stream. And like the default stream is associated with the integer 0, so when we pass a 0 here, then we will submit it to the default stream. And if we don't want to submit it to the default stream, then we just create stream objects, like a CUDA stream t object, and we create, like for every stream and for every queue that we want to submit into, we create a stream object, and then we pass the stream object to the kernel call, to the parameterization of the kernel, and then only by that, and without using any multi-threading, the kernels will run asynchronously. So each kernel will basically run in its own stream. Like here's an example of the different execution modes. Like this is actually a very simple kernel that I programmed. And now I'm calling it here, and I'm submitting the kernel, and I'm calling it 8 times, and I'm submitting it to the default queue. And as you can see here, like there are certain functions, like the program that I coded actually performs a malloc before the kernel is called. And then we can also see that there is a the context creation and device reset. And we can see that the kernel actually overlaps with that. Like we're calling the kernel 8 times, and the kernel execution is actually overlapped with the runtime API call here. This is what the profiler reports. And what we also can see that the 8 kernel executions, they happen serially. Like we have one kernel execution, one after another, like 1, 2, 3, 4 through 8. So this is what happens when I submit to the default queue, so to queue or to stream 0. And when I submit to separate streams, then you can see in the profiler that the CUDA runtime is actually able to overlap the various kernels without me creating any threads or anything, just by using those stream objects. And this is the way that we would make use of the asynchronous host interface with CUDA. Like, there are several ways of synchronization. Like, for instance, when we use memcopy in a stream, then in that stream, the kernels that are currently running would be synchronized. There's actually a memcopy async function, and the memcopy async function will return immediately, so it won't block CPU execution. So then there's also the CUDA device synchronize function that we saw earlier, which is basically a barrier and will synchronize the whole device. So there are synchronization primitives, and memcopy usually synchronize implicitly, like depending on how we call them. But the memcopy call will make sure that the data that is actually called is also available, so that prior kernel calls actually finished. So another topic that we're very briefly going to discuss in the context of streams and of the host interface is that of measuring kernel execution time. And the problem with measuring kernel execution time is that when we submit a kernel or some other asynchronous CUDA call to a stream, then execution immediately returns to the CPU. So we cannot just easily profile that with a conventional profiling tool. And there's of course a pragmatic solution, like we could just enter a CUDA device synchronized right after the asynchronous call. But obviously this defeats the purpose, because usually our program builds upon asynchronicity, and by stalling the GPU execution pipeline, we would generally measure something else than as if we were to have our kernels run in parallel. So a better way to do this is to use the CUDA Event API. And the CUDA Event API basically sees us entering two tokens in the command stream, like what we formerly called the command stream when we talked about GPU architectures. And we enter one token into the stream right before the kernel or the kernels that we want to measure. Like, we can just measure the time between arbitrary commands, and then we enter a second token right after the execution finished of the commands or of the kernels that we're interested in. And then we're measuring just the time between those two events with a dedicated function that is called CUDA Event Elapsed Time. And that way, by using tokens, we're basically able to measure the time without doing any synchronization other than in regard to the two events. Like in code, this would look something like this. Like, we would have those CUDA event t variables, and we would create them, and then we would record the first event, like the start event, before the kernel call. And here I'm only showing a single kernel call, but we could actually have a bunch of them, like we could call 2 or 3 kernels or whatever. And here we're only interested in measuring the execution time of that single kernel. So we record a second event, the stop event, right after the kernel call finished. And then we synchronize on the stop event, and then we measure the elapsed time. So eventually we have to free those objects, like we do this with the event destroy function. And this is the way that you would measure kernel execution time with the CUDA event-based API. So this is a very lightweight method to measure execution of asynchronous CUDA calls. Like, in general, if we wanted to profile our application, there are actually better means to do this. Like, for instance, the visual profiler and the images I showed you earlier, where I showed you how my asynchronous kernel calls were executed in parallel. Those images were directly taken from the visual compute profiler. And there are also better profilers, even like the Nsight profiler. So there's a bunch of profiling tool. But the event-based API is actually a pretty lightweight method of measuring CUDA execution times. And it's good to be aware of this method of measuring time. And we generally don't have to rely on synchronizing the whole event if we, in a lightweight fashion, want to get an idea how long kernel execution takes for a certain kernel. So, and you will have noticed that we're already discussing miscellaneous topics from the CUDA API. And one such miscellaneous topic is interoperability between CUDA and between other graphics APIs. Like, CUDA in general is a GPGPU API, and CUDA doesn't supply us with any facilities to perform rendering. Like, we can write a renderer of CUDA, of course, but we cannot just like use the raster engine from within CUDA. So this is not exposed. And if we want to render our data that we maybe simulated with CUDA before, then we have to hand over execution to a graphics API, like for instance OpenGL or DirectX. And when we do so, and we are staying on the same GPU, like it's perfectly viable to use two different GPUs for the simulation and for rendering. But if the GPUs are the same, then it makes sense to not perform any device to host and back to the device copies. Like in a naive way, you would perform the computation on the GPU, then you would copy the data to the host, and then would fill some OpenGL buffers on the host and have OpenGL eventually copy the data back to the device. So this is, of course, what we want to avoid. And therefore, CUDA supports what is called Graphics API Interoperability. And in particular, we can share certain resources between CUDA and between the Graphics API, like for instance vertex buffers or pixel buffers. And we only have to make sure that when we use a common resource, that when one API has mapped the resource, that the other API doesn't have the resource mapped at the same time. So here's some code that illustrates how that works for pixel buffer objects, so for buffers that pixel data goes into. And CUDA has this notion of what is called a graphics resource. So we would first just create a graphics resource that is shared with OpenGL. And we would pass it some OpenGL handle that is associated with the pixel buffer object. And when we use the graphics resource with CUDA, then we map the resource, and then we obtain a device pointer to the resource. Like with CUDA, we always had this device pointer metaphor. And this is the same with shared buffers. So when we have a shared buffer, then we also obtain a device pointer to that shared buffer. And then we work on that buffer with CUDA, like we maybe write some pixel data into it. Maybe you have a ray tracer that outputs pixels and writes them to the shared resource. And then in the end, we unmap that resource. And then we hand it over to OpenGL, and OpenGL would do OpenGL things to map that resource and to maybe render the pixel data to a texture or so. So CUDA supports this interoperability mode, where you can share buffers between the two APIs, and whatever copy happens there under the hood, like this is an implementation detail that we don't know, is presumably pretty lightweight. So another miscellaneous topic, but is actually quite helpful, is the Thrust template library that comes with CUDA. Like when you install CUDA, you also install the open source template library Thrust. So this is a C++ library. And the Thrust library actually provides lots of very helpful facilities to make use of the CUDA API. And those facilities are implemented on top of the runtime API. So for example, Thrust provides us with a standard template library like interface, where we can have vector data structures, and those vector data structures use RAII, so the resource acquisition is initialization paradigm. So for instance, there are the host vector and the device vector, and host and device vector, they map memory regions on either the host or on the device, and they allow us to easily copy between the two memory regions. So the Thrust host vector, for instance, is a template where we can tell Thrust what data type we store therein. And the host vector is very similar to an STD vector, only that it has some interoperability with the device vector. And the device vector basically wraps CUDA malloc and also wraps CUDA memcopy, but also wraps CUDA free. So when we create a device vector, then the device vector will make sure that there's enough device memory allocated to the data structure. And we can also, we can pass the constructor of the device vector, we can pass it a host vector, and then the Thrust API will fill the device vector with the data from the host vector. So there are those simple copy semantics, and then there's RAII, which means that when the device vector goes out of scope, like this vector d numbers here will eventually go out of scope when this bracket here was reached, and then will call the destructor of the device vector class, and that will cause a call to free. So there are those convenience data structures that can be used with CUDA code, and all of this is interoperable with CUDA code. And then there are lots of algorithms that can be used. For example, there's a quite decent sorted implementation, like there are merge sort and radix sort implementations that can be used right away. There are other algorithms such as copy, for instance, that allow us to copy from the host to the device or vice versa. And also lots of other algorithms that are quite similar to the algorithms that are provided by libraries such as the STL or maybe by Boost. So for us, it's definitely worth a look, in particular for those typical routines that you don't want to implement yourself when you write high-performance code. In particular, Thrust is a host-side API, so you call Thrust algorithms from the host, and behind the curtains, Thrust might or might not do some GPU things. So when you, for instance, call Thrust sort, then Thrust will dispatch those calls internally to some CUDA kernels. As a matter of fact, Thrust isn't a mere CUDA API, so you can also have different backends. There's, for instance, a backend that would just use CPU threads. So for whatever this is worth, when you use Thrust in your application, well, so the default mode for you would probably be that you use the CUDA backend of Thrust to make use of the GPU, but there are also different backends that can be used, and the algorithms potentially being implemented on top of those backends. And let's have a quick look how the ASXP example that we were discussing throughout the lecture would be implemented with Thrust. So I will present two variants of the ASXP example, and the first variants will actually use two algorithms from the assortment of Thrust algorithms. The ASXP is a bit different in that A here is not a scalar but a vector. So it's actually a bit different than the usual ASXP example. So suffice it to say, this is an implementation where A is a vector and where X is a vector. So then we use Thrust transform, which will iterate over those two vectors. Like we passage those two vectors, and the device vector was previously filled with data. And then we have the transform algorithm iterating over those two vectors, like over the two ranges defined by those two vectors, given by the vectors begin and end iterators. And then we have the transform operation apply the multiplies functor to the items from those two vectors. So we have what essentially will result in one CUDA kernel call, like internally Thrust will dispatch this to a CUDA kernel call, and we'll call this functor which will multiply the items from the vector X and the vector A, and we'll store the result in A. So and then we do the very same thing with what is already in A, so with this temporary result that's now stored in A, and Thrust transform will return execution back to the CPU as when that kernel call finished. And then we basically call the second kernel, like by calling Thrust transform again. And now we transform the vector by just adding what is already in A, we're adding it to Y. And for that we use the plus functor. So one caveat here being that we're having to call two different kernels. Like we have first call Thrust transform one kernel for the multiplication, and then we call a second kernel for the addition. So that might have certain performance impacts. So there are actually other ways to implement that are a bit more complicated, but I'm showing them here anyway. So just to motivate yet another example of the Thrust API. Like what you can use in order to make Thrust perform the operation within a single kernel is the so-called zip iterator. Like what I'm basically doing here is I'm zipping together the begin iterators of the Y and of the A and of the X vector. Like the ASXP2 function here receives the same three vectors that the ASXP1 function received, and then I'm just zipping them together that they basically behave like a single operator. And then I'm also zipping the end iterators together, like I'm zipping the end iterator from the Y vector and from the A vector and from the X vector together, so that they together form a tuple. So I now have a combined iterator to the beginning of the three vectors and a combined iterator to the end of those three vectors. And I'm passing that to the for each algorithm. And the for each algorithm is basically like a for loop implementation, but running on the device. So this will call a kernel. And the kernel will run for each of the items that is iterated over. So we're now iterating over the tuples from the zip iterator. And we have to, like in order to do something useful, that we have to supply a functor. And I've written that functor myself. And the functor in this case needs to be a C++ or C struct. and needs to contain device code. And the device code, I'm passing a tuple, and for simplicity I made this a template so that I don't have to care about what the type is that I'm passing into that functor actually. And then I'm using the thrust get algorithm to get the various values from the tuple, like the get, and at position 0 will just give me the 0th entry in the tuple, and 1 and 2, and will get me the first and second values in the tuple. And then I'm just performing the ASXP multiplication, and I'm storing it to the tuple entry at position 0. So this is a bit more complicated use of the thrust API, but allows me to actually implement the ASXP operation within a single kernel. So there are various uses to the thrust API, and you should check them out for the specifics. And suffice it to say, the thrust API is pretty useful in certain ways, and it supplies many algorithms that you don't want to implement yourself. And therefore, it's very much worth a look if whenever you are in need of a certain algorithm, if it isn't supplied by thrust. So one thing that is a bit inconvenient about thrust is interoperability with custom CUDA kernels. So in general, this is supported, but the syntax for that is actually a bit arcane. So usually you have those device data structures like your device vector, and then in order for your CUDA kernels to interoperate with those, you cannot just pass in like a reference to the vector or a pointer to it, because the device vector will just not work on the device, but instead you have to like retrieve a raw pointer from the device vector, and then the device vector actually isn't a device vector anymore, but it's just a pointer to the data type that is internally stored by the vector. So interoperability with custom kernels is a bit complicated. Nevertheless, it is supported, so it can be done. But generally, the device data structures of thrust aren't usable from within device code. So the intended use of thrust is that you use the algorithms that are supplied by thrust, and that you use the data structures, and that you make do with those. And whenever you write custom kernel codes, then you also have the opportunity to use the functors that I showed you before that allow you to supply custom functionality to the transform algorithm or to the for each algorithm, for instance. So CUDA in general comes with a number of different tools. Like this is just like a list of tools that are important to us. Like most of them we already discussed, like the NVCC compiler or the occupancy calculator. There's actually a CUDA debugger, like a command line debugger. And anyway, debugging with CUDA is actually quite tedious, as you actually need 2 GPUs for that. And so when you're debugging a device program, then this will cause your GPU session to freeze, so you cannot use your desktop environment anymore or your terminal environment. And therefore you need 2 GPUs, one where you execute the CUDA program and the other one that you actually use for debugging and for displaying the state of the debugger. Nevertheless, printfs can be used in kernels, so you can place printfs there. You should be aware of that then every thread calls the printf function. So you usually will make sure that only certain threads will actually call printf, like by using the thread index variables that are built into CUDA device code. There's a bunch of profilers, like the Visual Compute Profiler, and there's also gprof, which is a command line tool for profiling. We already saw those earlier, like on some of the slides. And then there's NVIDIA Insight. And NVIDIA Insight is actually a bit of a more advanced profiler that actually allows us to profile into kernels. And in general, the integration of NVIDIA Insight with common IDEs such as Visual Studio, for instance, is a bit better than that of the other profiling tools. So there's a bunch of tools, and when you're doing some serious development with CUDA, you're most likely to use a couple of those tools, and you should be aware of their presence. So as you can see, we're already nearing the end of our discussion of the CUDA API, as we're like basically skipping through a list of pretty miscellaneous topics. And the last topics that I want to touch upon are a bit more advanced in that they tackle things like multi-GPU programming or dynamic parallelism, where you basically call kernels from within kernels. So those topics are a bit more advanced, and we'll discuss them very briefly just to give you an overview. So, and the first of those topics is multi-GPU, and multi-GPU basically means that we have more than one GPU attached to the host system via the mainboard and via PCI Express. So the mainboard just allows for multiple GPUs being attached, and then those GPUs, they use separate PCI Express lanes to connect with the host system. CUDA supports that quite seamlessly. So there are like a couple of built-in functions that can be used to make your CUDA application a multi-GPU application. And the most important function is the CUDA set device function in this regard. And when we switch devices, like when we switch the execution from one device to the other, then we use the CUDA set device function for that, and we pass it just pass it the index of the device. So the CUDA runtime will just enumerate all the devices that are installed to the system and will give it an integer starting at integer 0. And you can query with other functions, you can query the number of CUDA capable devices that are attached to the host system. And with CUDA set device, you can just set the active device, and then all CUDA kernels that are subsequently called until the next CUDA set device call will be executed on the device that is currently active. So it's actually pretty easy to use this multi-GPU execution mode. So in CUDA set device is also a asynchronous function, and we will later see how this can be put to good use to parallelize our multi-GPU application. And we can also use streams in conjunction with multi-GPU programs, and it's also actually quite common that multi-GPU programs are actually multi-threaded, where we have a thread per device that is used, and this is also supported by CUDA. And like if you have a very simple multi-GPU application, like if you have a kernel and we just want to run that kernel on multiple devices simultaneously, then we use the CUDA set device function. And like in this example, we're setting the device to 0, so the first device is active. And then we call the kernel, like there's a kernel that performs some work. And then we switch the device and call the second kernel. And actually, like if the kernel isn't like really fast, then the two kernels will run simultaneously. And this is because the CUDA set device function is asynchronous. So as the CUDA set device function is asynchronous, the execution will directly return to the device, and where we can call the kernel. The kernel is also asynchronous, of course. And as we're now switching devices with CUDA set device, we'll also make use of overlapping kernel calls here, and the second call will also run asynchronously. I mean, a non-trivial multi-GPU execution will usually see the two GPUs passing data around, like one GPU will share data with the other. And the function that is used for that is the CUDA memcopy peer async function. And the CUDA memcopy peer async function is an asynchronous function, as the name already says, and it has the same semantics as memcopy has. And now we specify not only the source and destination arrays, but we also specify the source and destination GPUs that we're copying from and that we're copying to. And we're submitting that to a stream because the function is asynchronous. And on certain GPUs, like not on all GPUs, this function will actually perform DMA. Like the function will perform a copy that doesn't actually involve host memory. Like as a matter of fact, this is only supported on the professional GPUs by NVIDIA. Like the Quadro or Tesla GPUs support this, and the GeForce GPUs, they will generally not support this. Nevertheless, the function is actually quite convenient. Like you basically just call the CUDA memcopy function, and it will perform a memcopy between the two devices. And even if the memcopy goes through the host, the use of that function is of course quite convenient because you don't have to take care of any buffers on the host that you have to allocate. Like when you're on an architecture that doesn't support DMA access between devices, or when the two devices are on PCI Express lanes that don't support peer access with DMA, then internally the memory will be rerouted through the host, but the user actually never sees this and never has to allocate any host buffers. So even if our code cannot make use of DMA, it's actually quite convenient to use this function. So one thing that I want to remind you of in this context is that PCI Express is not a bus. Like instead, PCI Express is more like a tree structure where you have multiple PCI Express switches, and those PCI Express switches allow us to communicate with different devices. And when two peers, like two GPUs, are connected to one PCI Express switch, then they, for instance, can potentially perform DMA. Again, when we have, for instance, GPU 0 communicating with GPU 2 in this example, then DMA might not be possible, and the actual latency for the memcopy operation might actually be higher. So in general, PCI Express is not a bus, but there's different memory access latency depending on where in the PCI Express tree we currently are. And when we're optimizing for multi-GPU execution, then we should take this into account to make sure that our application is optimized for multi-GPU. So another quite advanced topic is dynamic parallelism. And dynamic parallelism basically means that we call a CUDA kernel from a CUDA kernel. And you can use that for very basic recursion, but you can also call another CUDA kernel from within the kernel. And the feature that this is very similar to, or that is actually derived from, is the indirect rendering or draw erase indirect features from the graphics APIs. And it's a bit of an esoteric feature actually, but it can be helpful in certain situations. For example, when you do something like adaptive grid refinement. And the idea is basically that you have a kernel, and you'll to begin with you call that kernel from the host, so that it starts running at some point, and then within the kernel you just call the kernel a second time or maybe a third time and so on. And in order to do so, you have to again configure the kernel with the block size and with the number of threads, so with a grid. And that grid is quite often a subdivision of the current grid. So it's quite typical that you have like a grid, and then you take one cell and then you refine that cell so that it becomes basically like a quad tree when we're talking 2D grids, for example. So the idea here is that you can like basically run another grid of threads without actually having the host being involved in this. So there are certain situations where this actually can be quite helpful, like in particular when there is some potential performance gain from a different subdivision, but that performance gain doesn't actually rectify a communication back to the host. So the feature is actually a bit esoteric, but it's good to know that it is there. And like the example from before showed a recursive kernel call. This is not a necessity, so like you could have called any other kernel from within the kernel. And with that, we're already at the end of our discussion of the CUDA API. And let us briefly recap. Like CUDA is a vendor-specific GPGPU API, and there are other GPGPU APIs. Like in particular, there's OpenCL, but also Vulkan or OpenGL. And when you use OpenGL or Vulkan, those are primarily graphics APIs, but they allow for a dedicated code paths where you submit compute commands via so-called compute shaders. So there are alternatives to CUDA, and we basically learned CUDA because of simplicity, because it's a much more simple API than all the other GPGPU APIs. So CUDA exposes the memory model of modern GPUs, and we learned a lot about that actually. Like we learned about global memory and about shared memory. And the whole paradigm that is implemented by CUDA, like with those many threads and with latency hiding, because memory access operations have really high latency. We learned about that, and that's pretty typical for a CUDA application, and it's important to keep that in mind, like how that works with CUDA, because this is actually also a characteristic for how other GPGPU APIs operate and for their underlying principles. CUDA has this convenient mode where we can use a single sort model for both host and device. So other APIs actually don't have that. And this is part of what makes CUDA pretty convenient to use. And actually CUDA has gained a lot of popularity in the HPC community due to this API that is fairly easy to use. And that actually also gains lots of popularity to NVIDIA, who now actually very popular in the HPC community. There's lots of literature out there on CUDA, and I just only picked two of them, and the most important one arguably is the programming guide. So most of the examples that we saw can actually be comprehended by looking at the programming guide. And then there's also a book that I picked out. Like I guess there's a bunch of more books, but this is actually a book that I was able to take a look into. So I'm familiar with this book, and it's quite decent. And so I would recommend it. And there are lots of resources out there, also internet resources that help you to learn the CUDA programming language. So, and it seems that time has actually advanced a bit more than I thought. And I'm gonna end the lecture for today. And next week we're gonna wrap things up, where we'll finally gonna talk about sorting on GPUs.